Hey, APStat. So here we go. One particularly important family of density curves, so density curves from the last video, are the normal curves. And they describe a normal distribution. And it's curves that a lot of times people say the normal curve, but it's the same shape, but it can be a lot of different kind of widths and heights and positions and so on based on a couple of key features. So the shape of all normal distributions is symmetric, single-peaked, and bell-shaped. So we have that kind of curve, but these are both normal distributions down here. The center can be different. The mean, so the mu is the center of that distribution. It's a symmetric distribution, so the mean and the median will both be the same for these density curves. It's located at the midpoint of that and is the same as the median. The spread, or variability, it kind of affects the width, and that's some of the biggest things. So maybe this mean over here is higher than that mean, but the biggest thing we can see between those is the spread of these distributions. They're same overall shape, but the standard deviation helps us figure that the width of that normal distribution. So really those are the two key features that define different normal distributions, is where are they centered and how spread out are they. After that, we know exactly what curve we're talking about. So the normal distribution is described by a symmetric single-peaked bell-shaped density curve called a normal curve. Any normal distribution is completely specified by two numbers, its mean and standard deviation. So why are normal distributions important in statistics? There are a few key reasons. Normal distributions are good descriptions for some distributions of real data. Distributions that show up, it just kind of shows up naturally sometimes, right? And so test scores can be that. If we repeat careful measurements using the same kind of repeated over and over and over again, we end up with a kind of a normal distribution, a little bit higher, lower, and things like that. And then characteristics of some biological populations. This distribution kind of happens just naturally in some things that we observe. But there are more reasons. It's not everything is going to follow that nice normal distribution. Normal distributions are good approximations for the results of many kinds of chance outcomes, like proportion of heads in many tosses of a fair coin. So kind of crazy, if you just flip a coin over and over and over again, the distribution of possible outcomes, eventually, if you flip it enough, ends up falling into that normal curve distribution. So randomness, chance, actually ends up falling into that normal distribution. And many of the inference methods in our later chapters are based on normal distribution because they use that chance, and it's not just the coin flip, it's lots of other chance, ends up falling into this bell-shaped normal distribution. So it shows up sometimes naturally, but a lot of other times it's chance-driven, where even if the thing you're dealing with doesn't follow a normal distribution, if you leave it up to chance and repeat that process, that variability, that randomness ends up following a normal distribution. So very useful distribution that we'll use a lot, especially later on in the class, but we're gonna focus on it right now. All right, so all normal distributions have these following proportions in common. They call this the 68, 95, 99.7 rule in our book. Other books will call this the empirical rule. You may see it referred to as that. Maybe that is better named, but this one definitely tells you what's going on. So the rule is this: within one standard deviation of the mean, you'll find 68% of the values. 60%, 8% of the entire distribution always falls within one standard deviation of the mean, and that's true of all normal distributions. And because we're standardizing, we're thinking about these as a standard deviation from the mean. That's actually a z-score. It doesn't matter what your mean and standard deviation are for your data set, that will be true if you kind of figure out in terms of z-scores. 95% is always within two standard deviations, and 99.7, not all, but a lot of it, 99.7% of the normal distribution is within three standard deviations of the mean. There's just a little 0.3% that ends up in those outer tails. And this curve, so this is a density curve. The area below this is 1, so the area is 100%. And that curve does stay above the x-axis, and it does really have asymptotes here, so it kind of theoretically goes on forever, even though in reality that's often not realistic that you can go on forever. But this curve, the way that formula actually works for it, it theoretically does go on forever. So really important though, those numbers only apply to normal distributions. It does not apply to other distributions. Once you start calculating z-scores for some other distribution, you can't say, oh, well, 68% is within one standard deviation. No, just normal distributions is what that rule applies for. There may be some other distribution, but that's where we will apply this one. So all normal distributions are the same if we measure in units of size standard deviation from the mean. So that's z-scores. So if we convert it into z-scores, we end up kind of getting to a standardized normal distribution. So right now we've got this ITBS vocabulary score. Apparently followed approximately normal distribution. Looks like the center was there at 6.84. Seems to be they're labeling that one standard deviation away and so on. So if we convert those values into standardized scores, if we take each of those values, this 8.39, subtract the mean, divide by that standard deviation, we'll convert that into a z-score like this, into a z-score of 1 and z-score of 2 and so on. And so we can standardize our distribution, get a standard normal distribution where it's just how many z-scores you are away. And so this particular 6 here, that was, if we figure out that difference, if we do 6 minus 6.84, get that that's negative 0.84, divide that by the standard deviation, apparently that works out to be a negative 0.54. That's about a half a standard deviation below the mean, a negative 0.54 for that z-score. So the standard normal distribution is the normal distribution with a mean of 0 and a standard deviation of 1, and it's basically just showing z-scores. 1, 2, 3 standard deviations above the mean, 1, 2, 3 standard deviations below the mean, and everything in between.